Hello everyone. Today we'll discuss a very famous supervised learning algorithm called linear regression. Let's start. In the previous lecture, we tried to cover these points. We discussed what is machine learning and its types. We also saw the further categories of supervised learning, that is regression and classification. In this lecture, we will discuss a very popular regression algorithm called linear regression. The content of this lecture would be like this. Before going to the definition of linear regression and its implementation, we will first see what do we mean by training data and testing data. Then we will discuss a very famous concept called curve fitting. And finally, we will try to understand linear regression algorithm with the help of one example. Before discussing linear regression algorithm, it is important to first discuss training and testing data. When the data set is taken for the supervised learning task, it is primarily divided into two mutually exclusive data sets called training and testing data sets. This foundation is critical for understanding how the algorithms learn and then evaluated later. The training data set acts as the initial playground for our learning algorithm. Here, we introduce the algorithm to the data, allowing it to learn and adapt. The better the quality and relevance of this data, the more accurately our algorithm can model the problem at hand. Training is about guiding the algorithm to discover the relationships within the data, optimizing its internal parameters, known as coefficients or weights, to predict the outcomes accurately. It might seem technical right now, but as we will proceed further, it will become more and more clear. After training process, a separate set of data unseen by the algorithm during its training is presented. We call it the testing data set. This step is the measure of reliability and assessing how well our trained model can apply its learning to the new unseen data. Testing evaluates the algorithm's performance and verify the accuracy of its predictions. It also tells us whether the learning has been effective and ensures what the model is not just memorizing the training data but is genuinely understanding and generalizing. So if the performance of the model is good on testing data also, it means that there are high chances that the model will work very well for real-world applications. Let's take one example to understand the training and testing data in a better way. As you can see here, we have the overall data set taken from some task from the historical records. It might have multiple rows and multiple columns. It is a supervised problem because once again we have the x and y pair here. So out of overall data set, we divide that into two mutually exclusive sets. The first one is your training data as mentioned here, and the next one is the testing data. So at the initial level, we supply only training data to our algorithm. Algorithm learns and tries to establish the relationship between independent and dependent variables. And later on, we supply only this part of testing data to the algorithm and check what kind of predictions it is making. Whatever the predictions are, we then compare it with the actual values. If the predictions match with the actual values, it means the model or the learning algorithm is doing well in the prediction. If they do not agree, it means the model is not doing well and maybe we need to change the model. Let's take a more realistic example. We have seen this example in the previous lecture also. It is on the basis of manufacturing cost and advertisement cost. We want to predict how much sales we can expect. And let's say we have data available to us from 1991 to 2020. So we have 30 years of data. To divide that into training and testing data set, we consider major part of the data as the training set. So maybe this is our training set, which contains large portion of the overall data set. Usually 70 to 90% of the data is taken as training data set. And from this overall data set, we took out some examples, maybe 20 to 10% of the overall data set, which works as the testing data. The algorithm will try to learn only by looking at the training data set and then later on tested on testing data set. Once again, during the testing, we do not supply the actual values or the dependent variable. We only supply the independent variable and see what kind of predictions we are getting. And then we try to compare the predicted values with these actual values. If they are close to one another, it means the algorithm is doing well in the prediction. Otherwise, we need to make modifications in the model. So let's discuss the major algorithm for today, which is linear regression. Linear regression is a very famous and widely used algorithm in the domain of supervised learning. The algorithm tries to identify the relationship between one or more independent variables and a dependent variable. This process involves identifying how changes in the independent variables influence the dependent variable. To achieve the same, linear regression attempts to fit a specific curve to the given data points. This curve represents the best approximation of the relationship between the variables. Once this relationship is identified, predictions about the dependent variable based on new values of the independent variables can be made. There are many proposed algorithms for curve fitting, but the most well-known method is least squares. Here, we search for a curve such that the sum of squares of residuals is minimum. By saying residual, we refer to the difference between the observed sample and the estimation from the fitted curve. Let's try to explore it further. Let's consider these two scenarios. In the first scenario, the relationship between these two variables is linear in nature. But not all the data have linear relationship among its variables. In the second case, as we can see, the relationship here is not linear but non-linear. So the objective of curve fitting process is to identify the right curve that can tell us the relationship between different variables. As you can easily guess, in the first case, there is a linear relationship which can be better represented with the help of the line. And in the second case, a parabolic relationship would be better fit to represent the relationship between the variables x1 and x2. So, curve fitting is the process of identifying the right curve for the given regression dataset. Let's see a specific method of curve fitting which is called least square method. There is some maths involved here. Let's try to explore what is the meaning of these equations. Let's say I have this data set where I have been given x and the corresponding value of y is also available. And I want to fit a curve that tells me what is the relationship between x and y. Let's say I want to represent that with the help of a line. So fx here represents a line. When we draw the line here, obviously not all the points will fall on this line. Some may fall on the line exactly as this point. Some might be very closer like this point, but some might be really far away, something like this. So here the difference between the point and the line, as seen by the green line here and here, is the amount of error. Let's try to understand that in a different way. Let's say for a given point x1, y1, the corresponding prediction that I get from this line is fx1. So fx1 is the estimated value, the predicted value for the value x1 as independent variable, but the actual value is y1. So we can say that the difference between the actual value and the predicted value is the amount of error due to point 1, x1 and y1. Similarly, E2 here represents the difference between the actual value y2 for the second point and the corresponding predicted value fx2. Similarly, if we calculate errors for all the points, then maybe for the nth point the error can be represented as En. So the total error becomes summation of E, but here in the case of least square method we consider the square of errors. So the overall objective becomes to somehow minimize the sum of all these errors, also called residuals. In the expanded form, it can be written like this. It is the sum of the differences between the actual values y minus the predicted values fx. If we want to minimize that or look for the coefficients for which we get the minimization values, the standard process is to differentiate the error term and put them to 0. So here these signs, they represent the differentiation of E square with respect to different coefficients of the curve. Let's try to understand that further with the help of one example. Let's say that I want to fit a curve fx which is given by a plus bx. It represents a simple line where a is called the intercept term and b is the slope of the line. When I put it here for the first point, y represents the actual values and a plus bx are the values that I will get after the prediction. Then E square can be the overall sum of squares can be given like this. So there are two coefficients here in my curve, A and B. It suggests that we need to differentiate the error term with respect to A and with respect to B. With the help of calculus, we can get the differentiations like them, this and this one, and we put them to equal to 0. When we try to solve these problems, these two equations, we get the set of these two equations. They are also called normal equations. Now we have two variables to identify, two coefficients to identify, and we have two equations to calculate their values. It can be done easily now. And the value of a and b after solving these examples, these equations would be the values that will give us a curve fx, which gives us the minimum amount of error when fitted on this data set. Let's try to understand this further with the help of one example. Before going into the example, let me also tell you that the normal equations can be extended in order to entertain the higher order polynomials. Because let's say I do not want to fit a line here, but rather I want to fit a more complex curve like this or even like this. In that case, the normal equations would be 4, because we have 4 variables to identify A, B, C and D. So as you can see here, the set of normal equations can be generalized further in order to entertain higher order power of independent variable x. Let's try to solve one example in order to understand linear regression in a better way. Let's say I have these 3 points. The first point represents the x value. So this is x1, x2, x3. And we have the pair y1, y2 and y3. So given these points, I want to implement linear regression on that with the help of least square method, and I want to fit a line there. When I say regression line, it means the function I want to fit here is a plus bx. It does not contain the quadratic term. How can we do that? Let's see it. First, for the given curve, we have to write the normal equations. They are these 2 lines. It means we have to calculate n, we have to calculate summation of xi, summation of yi, summation of xi once again, summation of xi square and summation of xi multiplied with yi from the given data. So this x is given to me, this y is also given to me, the corresponding y. So as you can see here, the summation x would be 2 if we add all the x values. Similarly, summation y would also be 2 if we add all the values given here. Summation xy would be 9 because we will first multiply x value with the y value and then add all of them together. So for example, minus 2 multiply with minus 1 give me the value 2. That is the multiplication of x and y. And finally, we have to calculate x square because we also need that in our equation. X square means the squared term for x. So for minus 2, once again, the x square value would be 4. Similarly, for 1, it would be 1. For 3, it would be 9. And sum of all of them will give me summation x square, which is 14 in this case. So out of these 2 normal equations, when I put the values of summations, I will get the value 3a plus b times summation x. We can see summation x is 2, so 2b is equal to summation y, which is once again 2. The next equation would be summation a, which is 2a plus b times summation x of x square. So summation of x square is 14. So we have here 14b is equal to summation of x and y, which is 9. So after solving these two equations, we will get the value of A and we will get the value of B. When we fit the values of A and B once again in our curve, then we will have the regression line that fits this data with the minimum squared error, or in simple words, with minimum error. So after solving these two equations, as we have seen in the previous slide, the value of A turned out to be 5 by 19. I think the value would be around 0.26 when we solve it further. And the value of B would be 23 by 38. And the value of B, I think, would be around 0.6. So my fx, or sometimes we also call it y dash or even y cap sometime, represents the estimated value of y. Remember, whatever value of y we will get out of this line is not the exact value, but our prediction of the y value for a given value of x. We can also see how this line fits data -2, -1, 1, 1 and 3, 2. Once we get this line, then the next obvious question is, what is the purpose of this line? The purpose is, for the unseen example where I know only the x values, not the y value, I can put it here and I will get an estimated value of y. For example, when x is 4, then I can calculate my y dash or y cap as 0.26 plus 0.6 times the value of x, which is 4. The value I will get would be an estimation of my y value. So what is the next step? Let's say we have fit the line, fit the curve in general, and for our specific example, we have simply fitted a line here. When I get this line, then what is the next purpose? Next step. The next step is, once we have got the curve, now we have to test the performance of this curve on the unseen test data. Remember, we discussed earlier, whenever we have data, we divide that into two categories: training data and testing data. We supply only training data to the algorithm and we do not show it the test data. This is the time now we bring our test data into picture, and then we try to test how good my algorithm or the learned model is performing on this unseen test data. If it performs good on that, then my curve is okay, my linear regression algorithm is doing good. But if the performance is not satisfactory, in that case we need to choose another curve. That another curve could be a quadratic curve, or it might contain much higher order polynomial terms of the independent variables. It is also important to note that depending upon how many coefficients we have in our curve, the number of normal equations, they become larger and larger. There is a compact way of representing the same like this. Here x represents the independent variables matrix and y represents the vector of actual values. So the algorithm goes like this. First, we define a matrix of one column which has only one independent variable, and another matrix X of size n cross p, where p are the number of independent variables and n is the size of the data sample. In the step 2, we add one more column of ones as the first column in X, which makes the overall X matrix of the size n times P plus 1. And then we try to compute this expression, which will give us the values of the coefficients of the curve. Xt is the transpose multiplied with x once again, the inverse of overall multiplication, then once again multiplied with x transpose, and then finally multiplied with y. This compact form makes our life much easier. We need not to calculate too many normal terms. We calculate simply this expression and it will give us the results. We will see one example related to that also. Before we go into the implementation part of linear regression, to conclude, in this lecture, we discuss linear regression algorithm. We also discuss what is training and testing data. Linear regression is implemented through curve fitting process, and least square is the most popular approach for the same. We also discussed a compact form of implementing the regression algorithms. In the next lecture, we will see the implementation of linear regression and some other related topics. Thank you.